Hello, everybody. Okay, so announcements. For those of you who watched the pre-recorded lecture, sorry, I was hoping to be back on track, but I've just literally had no time to do them lately. I will try. But there's other more important stuff. When I looked at the feedback, people generally feel like the webcasts are not as good, but they're good enough. And so at this point, when we're trying to get the homework and projects out, I'm focusing on that. Another thing, so project 2A, 2B, for those of you who spent a lot of time and did not get points because of an error on your part, I think it's unreasonable for you to get almost no points if you put in a ton of effort. Details to be discussed. Question for you. If you had two choices, which would you prefer? Now let's assume your final score is the same either way, because it's going to be designed that way. One approach is try again, where you get one more submission to fix your bugs and learn something. And that would be maybe by the end of our week or something. The other approach would be just let it go, where we'll do some manual grading, give you some effort points, and it'll be added to your autograder score. Don't worry about the details. Just if you had to pick between trying again and learning from your mistakes, or just letting it go and moving on, and assuming you'll get the same ultimate score, which would you prefer? So let's do this, just because I want to get a rough sense in this room. And if you got all the points, you can still vote. Just imagine that you're, or almost all the points, just imagine if you didn't. Okay, so if you want to keep answering, go for it. If you want to discuss this further and try and convince me, come to my office hours after class. All right, moving on. You're roughly evenly split. It's like leaning a little bit towards try again. Okay, so project 3. It's like phase 3. Sorry, that's what I meant to say. Phase 3 of the course is kicking off today. This is going to be the algorithms and software engineering oriented phase of the class. Because you have, it's the end of the semester, we're all getting a little tired. And we have homeworks and projects we have to be working on. I'm slowing the roll of the lectures a little bit, and that we're going to have this sort of tricky Monday, Wednesday technical content on algorithms, same as usual, no harder than usual. And then Friday I'm going to talk about software engineering and real-world issues, and those lectures are going to be inspired by a book by John Osterhout. If you want to get it, it's pretty good, short, fairly cheap, called A Philosophy of Software Design. And that material, it's just not really something I can test you on, so it's not going to be something where you feel like, oh, I need to know crucicles and prims and the runtimes and da-da-da-da-da. I hope that the Friday lectures will feel more like we're hanging out, okay? Less like it's material that needs to be learned, okay? Now, that said, we have some assignments in this phase that we're going to use this software engineering idea, but it's not going to be quite the same as usual, where it's like a deep connection between lecture and assignments. So in this phase, we have homework 4, which is due Wednesday. And if you already know how A-star works from before the midterm, it's just a tiny tweak to that. I believe there is a bug in the homework 4 autograder where it can be a little non-deterministic. So if you're occasionally failing the integer hop test non-deterministically, I think that's a bug. So not yours, it's ours. Then we have project 2C, which will be now that you've built your A-star algorithm and your KD tree and your PQ, you'll combine all those things into a mapping application. So in browser, it'll be like a street map of Berkeley. And I hope it's not too big. My main job tomorrow and late tonight is just making sure that this project fits before this Wednesday. And then lastly will be project 3, which was a popular project from last year, where you're going to build your own thing. So now we're just kicking the training wheels completely off, and you're going to kind of decide what you're doing. So in project 2, we made you prove that it works, at least 2A and 2B. In project 3, we're going to give you freedom to decide what you're doing in the first place. So I hope you think that's cool, and be aware this is a partner project. So any questions before we jump into sorting? I ran over here, so I'm still catching my breath. Yeah.
So how is project 3 graded?
So project 3 will be graded. There's an auto grader, but the main part of your grade comes from a checkoff, which will be in lab the last day of lab. All right. Cool. So let's talk more about algorithms. So to be honest, we have actually been doing algorithms a lot lately. Graphs, we've been talking about Dijkstra's, we've been talking about A-star. But we're going to go to a more elemental and basic type of algorithm, that of sorting. So you know what sorting is. It's basically I have a bunch of items and I want to put them in order. And I'll say that that's a useful task, clearly. So for example, you saw in some discussion section or other that if you sort items, or actually also in lecture, if you have items and then you sort them, you only need to look at adjacent items in order to find duplicates. So that's one reason that sorting is useful. It allows you to rapidly find duplicates in a list or an array. Another is if you sort items, they're in increasing order, so you can binary search. Or another example, if you sort your items, then you can put them into a balanced search structure, like, say, a binary search tree or a KD tree for later searching. So, I don't think I have to convince you that sorting things can be useful. Like in Excel, like sort by columns, I think you've probably done. Another reason we're going to study sorting, though, is that it actually is, by doing the same problem like 4 times or 4 lectures worth of just different ways of thinking about it, it's a case study for how problems can be solved. And unlike data structures where our goal is kind of tricky, like I have a priority queue, how do I build this? Now the problem is so simple and so elemental that I think we can learn quite a lot just by looking at how we would solve this problem. And we'll see that we use a lot of our data structures. So I'm going to define sorting a little verbosely. I'm taking this from Knuth's Art of Computer Programming, and he defines sorting as follows. So he says, I shortened his definition just a little, but it's close. So he says we have an ordering relation less than. Okay? We define a notion of less than on keys A, B, and C, and it needs to have 2 properties. One, it needs to be trichotomous. I didn't know that term before I saw that in Knuth's book, but he basically says exactly one of these 3 things must be true. A is less than B, A is equal to B, or B is less than or equal to A. Okay? And we also need it to be transitive. And any ordering with those properties he calls a total order, and you may know that notion. So then sorting is to rearrange or permute your items such that they are in non-decreasing order according to your less than operation. Okay? So that's sort. So for example, just to give you something you can sink your teeth into, let's say we want to sort strings by their length. So the length of a string, it obeys both those laws. Either string A is shorter than string B, or B is shorter than A, or they have the same length. And it is clearly transitive. And if we have the strings cows get going V, for this ordering relation, there are 2 correct sorts. Okay? Now, quick note is that when Knuth says equals here, that's not the same thing as the java.equals. Okay? This is equals in terms of this relation. So V is considered equal to get under this relation because the length is the same. Okay? So typically in Java, when we define an order, we're going to use a comparator or a comparable, or that is a compare method or a compare to method. And so, yeah, here you go. This is an example of how you would define one of these orders. This compare method compares the lengths of the strings x and b. Okay? And again, when Knuth says equals, he's not talking about dot equals. So any questions about the stage we have set? It's maybe a little more technical than we really need. I could have just said, you already know what sorting is, but decided to go a little deeper. Okay, great. Okay, next thing I need to tell you about is something known as an inversion, and this is an alternate definition of sorting. So we have informally some sense that it's not just that things can be sorted or unsorted, but there could be middle ground. So this array right here, is it sorted? No, like 8 shouldn't be in the middle, but it's like on the way, right? It's kind of sorted. We have 0, 1, 1, 2, 3, 4, so far so good, and then things get a little haywire. So to capture this notion that things can be partially sorted, we're going to use this term inversion, which goes way back to Gabriel Kramer, also the creator of Kramer's rule. If you've ever done any linear algebra and learned that rule. Anybody learn that rule out of curiosity? Was it in a circuits class? Or somewhere else? Where do you know it from? From what? Math 54. Where else? Calc 1. All over the place. I think it said Westworld at first. I was like, what? Is that in there? Anyway. Anyway, got some inversions here. And to give you some examples of what they are. So 0 and 1, these are good, right? 0 is less than 1. 0 is less than 2. 0 is less than 4. An inversion is basically considering all possible pairs. Here there are there are 55 possible pairings. We'll notice that some of them are wrong. Like 8 and 6 are wrong. 8 is to the left of 6, but if it was sorted, it would be to the right. And you can actually enumerate all of the errors. We have 8, 6, 8, 5, and 8, 9. And we have 6, 5, 6, 7. I'm sorry, 6, 7 is good. 6, 5, 9, 7, and 9, 5. So there are 6 total issues. Okay. So another way to think about sorting is, given a bunch of elements that are in some arbitrary order that currently has 0 inversions, we want to do some kind of operations. They could be swaps, they could be whatever else, so that we reduce the count of inversions to 0. Okay? Different way of thinking about sorting. All right. Any questions before we move? All right. Oh, midterm grades. Yes, good point. Sorry. Thank you. So midterm grades, I'm almost, everything's graded. I just need to make sure that the rubric's all good. So I'm just backed up. So we're pretty close. I just have a couple little grading issues where I need to think, like, is that a reasonable thing? All right. I'll try and do it tonight. If not, tomorrow. Tuesday's my full work day. Now. Alrighty. Tuesday, I'm hoping. Maybe tonight. All right. Cool it on the midterm. Oh, who graded it? Everybody. Not me. We had 50 people graded or something. So, yeah. The TAs. I did some grading, but not much. Okay, so runtime efficiency. 2 things I need to tell you about before we want to compare different sorting algorithms we come up with. And so we're going to talk about their time and their space complexity a lot. Time complexity is the runtime. I've probably used that term before, but if I haven't, I'm going to use it today just to get it into your vocabulary. For example, Dijkstra's is big O E log V. And we'll also talk about the amount of space that our sorting algorithms use, and we will call that the space complexity. Now, one quick note is we're only going to count the space that the algorithm needs to do its job, and we're not going to count the space needed to store the input. So, for example, a graph takes up V plus E space because you need to store the vertices and edges. This is in the adjacency list representation. But we don't count that as part of the space needed by Dijkstra's, because that's just what you already have. The space complexity of Dijkstra's is just theta V, which is the priority queue, the distance to array, and the edge to array. Okay. Well, these examples, or these notions of space and time complexity will become more clear as we do some sorting. Okay. So finally, 15 minutes in, let's talk about our first sort, selection sort. So we've already seen selection sort. We did it during our testing lecture. And the basic idea is you find the smallest item, put it at the front, and then fix it. And by fix, I mean you're sticking it there, so it never moves again. And then we're just going to repeat until all the items are fixed. All right, so let's check out a demo of this. So you've seen this, but you may not remember it since it was just in the middle of another lecture. And so the approach here is we have a bunch of items, and the smallest one is, you got to look at it. Okay. We're waiting. That's the thing we sacrifice in the modern world. Oh, look, I'm gonna drop discussion in midterm for now. We're talking about sorting. All right, so selection sort. What's the smallest item? 2. Good. All right, so what do? Put it at the front. How do we do that? I think swapping is a good approach. That's not the only thing you could do. So 2's at the front. Now the invariant is that everything on the far left is sorted, everything else is unsorted. What's the smallest remaining item? 15. You swap it with itself. Nothing happens. Okay. So next smallest? 17. Swap it. Okay, good. Next smallest? 17. Swap it, and so forth. And again, the nice thing about this algorithm, in terms of invariance and seeing why it works, is that everything that's gray to the left of the line, this virtual line here, they're all sorted. So if you keep moving the line over to the right, eventually you'll be sorted. So 19 swap, 26 swaps, 32 swaps. All right, any questions about selection sort? So we did a whole lecture where we spent the entire lecture implementing it and testing it. And so the runtime for this, if you recall, is n squared, because we look at all the items to find the smallest, then the last n minus 1, then the last n minus 2, and so forth. And the overall sum would be then just the sum of the numbers from 1 to n, and we get n squared. Okay? So that's basic selection sort. Any questions about that first sort, which you've already seen but may not remember? So I'm going to say this algorithm seems inefficient, right? Like the dirty, gross thing about this algorithm is you're continuously looking at a bunch of stuff you already looked at. You look at everything and find the minimum, and then you don't keep anything you learned around. You just say, I found the minimum, and I don't care about where the other ones were. That seems weird to me. So one way to approach this, one way to make it better, is let's keep a heap around so that getting the minimum item is fast. Okay? Now I'm going to do something a little strange. I'm going to use a max heap, not a min heap. Now that seems totally bizarre because we're trying to find the smallest thing. So keeping track of the biggest seems wrong. But the reason I'm doing it is that we won't be able to take advantage of a certain trick. Okay? So you could do it either way. You could do min heap or max heap, but I'm going to do max, and you're just going to have to accept that. So here's the naive heap sort idea. I'm going to take all my items, put them into a max heap, and then I'm going to throw away the input array. And then I'm going to create an output array, and then I'm just going to repeat the following n times. I'm going to delete the largest item, and then I'm going to put it at the end of the output array. Now this seems more complicated than it needs to be, and we'll see a better version in a minute, but I'm going to do this because it's so easy to understand when you see it in action. Okay, so, alright, let's go. We know how max heaps work. I'm just going to trust us that we know that. So here's all our items. Here's my input. Alright, I am going to put them in a max heap, and I'm not going to show you how that is done, because you already know that, as you've said. So here we have a heap which has all of our items, and they are in a max heap. Now, is this sorted on the bottom? No, not even close. In fact, you'd say it's counterintuitive, because now 41's at the front. That's like the absolute wrong thing to happen. That's fine. Okay. So now the algorithm is going to say, now that we have this heap from another lecture, that's how we know how to do this, I am going to, actually I have a question for you, which I forgot I was going to ask you. What do you think the runtime would be to do this, to insert all the items into a max heap? N log n, right? Okay, so I hope you'll agree that that's big O of n log n, because you're inserting n items into a heap, and each operation takes no more than log n time. So we can big O of n log n. Okay, that's step one. And now phase two of the algorithm is, now that you have the heap, let's take the top item, or the max item, and delete it and stick it at the end of my output array. So I have made now a third. So I started with an input array. I created a heap array. Now I'm creating an output array. So when I delete 41, it will go at the back. Okay? So this part is now sorted. And when I delete 41, you'll notice that this structure here, it changes in various ways. Like 41 left, 32 ended up here, 16 is here, and so forth. Right? Okay? This is the interpretation of the heap. How did that happen? Well, it's the usual rules. All right, so 32 is next. When we delete 32, it will end up at the end of my sorted array, and this is my new interpretation of my heap. And I could just keep repeating that process. It's the same thing you already know, where you do a bunch of heap deletes, and every time I delete one, we preserve my heap properties. And we end up with an array where the big items fill in from the right, okay, and so forth. All right. And so that is the idea of my heap sort. Okay. All right. So then, question. Hopefully, there's nothing too mysterious there. Question for you then is, what is the runtime of this algorithm? You toss everything in a heap, delete the items one by one, and I want you to give me the total runtime. So that's inserting, the time to build the heap, the time to delete everything one by one. By the way, these questions double as a chance for you to just reflect on what just happened. So, okay. So many of you came up with the correct answer. I said theta n log n. I'm not going to prove that right now, but I'll at least show you that it's big O of n log n. So the overall runtime, getting the items into the heap is big O of n log n, as we said earlier. Getting the largest item is always constant. It's always at the top. And each removal is big O of log n. And the reason I'm using big O here rather than theta is I'm acknowledging the fact that the heap is changing size over time. Okay, so we can clearly see, without thinking very much, that removing the largest item is bounded above by log n, But of course, some of the later operations will be fast. Okay? So the overall runtime, if we're considering we have building the heap, finding the minimum item n times, and removing the largest item n times, is going to be n log n. So if you'll note here, the reason this is constant and this is n is because these last two steps happen n times. Okay? Now, n log n is a lot better than selection sort. And then the space complexity is theta n, because we have to make these two arrays of around size n. Now, that's worse than selection sort, but I don't think it's that big of a problem. If I have an array of size n, then making another couple of arrays of size n, maybe not such a big deal. But you might disagree in some circumstances. And we can get rid of that extra memory cost with a little more fancy tricks. Now, a fun thing you can try and do is convince yourself that this is not just big O, but also big theta, but I will not do so here. All right. Here's an alternate version of heap sort. Is there actually any questions about this algorithm? Now, how do we avoid this theta in memory? What if I don't want to make a heap and then insert stuff into it and then take stuff out and put in yet a third array? Well, there is a version of this algorithm that is known as in-place heap sort, where you just use your original array and you use no additional space. Okay. How do you do that? Well, let's say I have an array of items. Is this currently a heap? Right? If you think of it as a heap, if you look at it, does this thing obey the heap property? There's a hint on the slide. It's not a heap yet. Okay? So what I'm going to do is I'm going to turn it into a max heap. Why max heap? Because that's what we did before. Okay? Still seems weird though that I did max, but it'll become very clear soon why we're doing max. So now that we're doing a max heap, we look at this array and we need to turn it into a heap. What could we do? Well, I'm going to now tell you about an operation I've never told you about before, which is it's a technique. If you did some of the old midterm problems, who saw something about heapification of arrays? Out of curiosity. Okay, so it's a procedure which I never mentioned in class, but it's a way to take an array and turn it into a heap in place. And the way it works is we're going to sync our nodes in reverse level order. Now, where did I get that? This is actually pretty deep. Okay? I'm just giving this to you for free, that if you go through the nodes and you sync them in reverse level order, then the result will be a heap. What if I sync them in level order? What happens then? What if I sync them in pre-order? What then? Well, that was actually one of the midterm problems this time, right? If you sync a heap with its nodes in pre-order, you don't necessarily get a heap. But this one, it's guaranteed to work. All right. So let's try it out. I'm just going to show you that it works, and you can maybe convince yourself later that it actually does. But let's actually see the process. So if I sync this item, which is the first item in reverse level order. Reminder, by the way, if you forgot what level order is. Sorry, I forget that you guys haven't taught the class 7 times, so you may forget these things. Level order is 32, 15, 2, 17, 19, 26, 41, 17, 17. Going level by level. So we're going the backward direction on that. So if I sync 17, it has no effect. There's nowhere to go. Okay? So I hope you agree with me that 17 is the root of a very small heap. Okay? 17 here, if we sync that, what happens? Nothing. All right? What about when I sync 41? Nothing. When I sync 26? Nothing. When I sync 19? Nothing. So those are 5 little baby heaps. Now finally something will happen. Maybe. Okay, when I sync 17, what happens? Nothing. All right, dang. Well, that's also the root of a heap. So I just want to make a note here. Because I've now sunk 17, because I had 2 heaps that were below me, if I now sync the root, it is guaranteed that the result will also be a heap. That's the part that's like kind of the proof that it works, though I didn't give you enough time to really think about it. So here I'm coloring these blue to let you know. These guys are all one heap, and I'm graying this out because, yeah, technically these are roots of heaps, but they're little heaps. Okay. So at this point, you can think of the bottom so many elements as guaranteed to be a heap. Now, quick note, I didn't actually change anything. Let's go back to where we started, right? You still have the elements 17, 19, 26, 41, 17, 17. So in fact, all we've done is nothing. Okay? We've just annotated. All right. Finally, let's do something. Okay, 2. When we sync 2, what happens? So this is a maximum-oriented heap. So is 2 the correct boss of a max heap? No. What's the correct boss? 41. Okay, so finally something happens. 41 and 2 swap. And now we know that since this on the left was a heap and this on the right was a heap, and now we've sunk the root, this overall data structure is also a heap. That's the invariant I'm relying on. So now I basically have 3 guaranteed heaps. We have my blue heap, my pink heap, and this one, which I'm not coloring because it's all on its own. So next, I guess, that's the question. So what happens next? What's the next item we're going to sync in reverse level order? 15. Now does something happen? Who should be the new boss? 19. Okay. So we swap 19 and 15, and now we have a big heap that's blue. So now we have a blue heap on the left, a pink heap on the right. And if we sync 32, the resulting object is guaranteed to be a heap. Now the property I didn't tell you, but you can convince yourself later, is if you have 2 sub-heaps and an arbitrary value at the top, and you sync that value, the overall result will also be a heap. I'm relying on that property, unstated on the slide, for this to work. Well, yeah, we're making it a max heap, but we're not necessarily done yet. So 32, we sync it. So what's going to happen? Who's going to take over? 41. Okay, so now 41 moves up, and since pink and blue go together, they become purple. We have one big heap. Okay? Now, a quick note is that because we're using the original array, we don't have enough room to leave an unused value at the front like we did in the earlier lectures, but that's okay. I mean, you don't have to have that. And so in this case, it's a heap. We just don't leave the empty spot at the front that we did in one of our tree representations. All right, so we have a heap now. Is it sorted? No. All right. Well, that's okay. We're going to do the same thing we did before. Okay. So this is an alternate way of getting a heap. Instead of taking the items and inserting them into a brand new heap, we're just doing it in place, and that avoided the need to build a separate data structure. We did it all in place. Okay? And you'll see it was just a few operations. All right, so now we're going to do the same thing we did before, where we're going to delete an item at the front and put it at the end of the array. So when we delete 41, we're doing something slightly different. Before we created an output array, and where do we put 41? At the end of the output array. Now what I'm going to do is I'm going to stick it at the end of the heap array in place. So I'm going to take this 41, I'm going to put it at the end, and basically the left so much of the array is going to be the heap, and the right is going to be done and used up. Okay? So this approach then, we put 41 at the end, because, okay, actually, question, when we delete the or the root of a heap, what do we promote to the top before syncing? The last item. So this is actually perfectly fine. This is like perfectly in line with what we did before. So we remove the president of the company, and we promote this last person up to the top, and then we do some syncing. Now I didn't show all the steps because you've already seen it before, but we took 17, put it at the top, and then sunk 17, and got this heap. Any questions about that, what I just did? Okay, so we do it again. We take 32. Who's going to be the new temporary boss? 17, and then we sync, and you end up with this result, and so forth. So all I'm doing is the same old process. Oops, okay, yeah. What'd I do? Okay, yeah. So I want you to try and do it, because if you understand this, you understand heap sort. So if you take 26 and you delete it, what will be the array after this delete? I'll give you guys a minute or two to do this. A minute. So 2 is the new temporary boss. Then what? Okay, so after the deletion, what we end up with is here. All right. So any questions about this? This is what I got. So 26 ended up at the unused part of the not heap part of the array. 2 was the new temporary boss. After syncing, we ended up with this. All right. So any questions about this? So a little, yeah, please. What's the runtime complexity of? Heapifying. So that's a good question. So I think I do that. If I don't do it in the next slide, then I'll explain it out loud. But yeah, I don't want to get there yet. Other questions? Yeah. Oh, so how do you... You still have to write down the level order was suggested as a reason why it'll take n memory, but I claim you don't. So when you do the syncing, how do you do the reverse level order? Well, you just call a sync method from n-1 to 0. So it takes no memory. Because remember, it's just an array. So you'd call like sync n-1, sync n-2, and so forth. Other questions? So it's intricate, right? If you hadn't really understood heaps before, then you wouldn't understand this. But because we have heaps as a basic building block, an idea that we can depend on, we're able to, without actually explicitly creating a heap or a priority queue object, we can do a sorting of our array. So that's my question for you then. I totally forgot I did this. All right. So let's think about, what do you think the time complexity of in-place heap sort is? I've already given you two of the pieces, so you need to think about what runtime you think bottom-up heapification has. So my question is for you now, instead. And so bottom-up heapification, by the way, is the name of that process. Sync the items in reverse level order. All right, I'm spoiling it. Okay, so bottom-up heapification, this is a way to think about the runtime. For that whole process, you're doing in-sync operations. Each item gets sunk, and the time it takes is no more than log n per sync. Because the root, in the worst case, will go all the way to the bottom, which will be log n time. So the overall runtime is in log n. And big O. You can actually show, by the way, for more, if you want to go extra crazy, you can show that you can give an even better bound, which is that bottom-up heapification actually is only linear time. And that seems a little strange, right? That if I'm syncing all the items in reverse level order and the root can actually take log time, how could the overall time be theta n? That's a pretty challenging asymptotics problem. It's actually not beyond the scope of what you might be capable of in this class, but I would consider it a very hard asymptotic question for this class. Okay? So I'm giving a big O bound, but you can actually show that it's theta n. And if you'd like, you can also show that overall heap sort in this case is theta n log n. I'm just doing big O of n log n. Okay? All right, any questions about this runtime? Okay. One advantage of big O, by the way, is it makes lecture smoother. Because if you can just bound above, you don't have to get the exact right thetas, right? So by doing big O, you can hopefully easily see that it's big O of n log n, but theta n, that would just take us another 10 minutes probably. All right. What's the memory or space complexity? I'm only giving you 30 seconds for this one, even less, as long as it takes me to type it in. And here, I'm talking about the version we just saw. Okay, one of my theta n people, talk to me. I want to know why. I want to know, I got about 50-50 theta n, 50-50 theta 1, a few others not. Theta in person. Anybody willing to go and tell me why? Just a guess. Anybody not have a guess? Yeah. Creating in spots for a min heap. All right. I'm going to say, no, I'm not. Actually, I'm not. I'm reusing the same array that I was given. So you're doing it in place. In other words, the algorithm is in place. So if you look at the steps of in-place heap sort, there actually was no point where I used any additional memory. Everything was always just operating on this array, and that's why it's actually constant. So the correct answer is constant space. Okay? All right. Okay. Any questions about that? The argument, the proof there is if you scroll through all these slides, there's only one array the whole time. Yeah. Shh. Okay, so that's a good point. If you have an array of size n, who cares about making another arrays of size n? That's a perfectly valid argument, and that's one of the reasons you might say maybe we don't care about the space complexity. The only case where you run into trouble is, let's say your array is like a gigabyte of data, then it is true that it's like not going to explode the algorithm and make it never complete, but it's annoying to have to allocate another gigabyte of space. So, yeah. But it's a fair point. It's not asymptotically different, but it's better to do constant than linear. Say again? Yeah, you could argue it's just a constant factor of 2. Yep. But we define memory complexity as how much you use that's extra. Okay? All right. Moving right along. So we got selection sort and heap sort. Let's talk about merge sort. We already saw merge sort, but let's think about it a little more. Actually, any questions? So selection sort was slow. Heap sort was an optimization of selection sort that uses a heap. In what sense is it selection sort? Well, it's selection sort in that we use a heap to keep track of the smallest or the biggest item. Yeah.
So basically, the best case runtime, how is it squared? Because we have to do
Why is selection sort best case n squared? Because you have to always go through all the items every time. Selection sort, if you look at the code, it literally goes through every item each time. Yes. One quick note. Remember I said that the max heap, it should become clear why using a max heap is smarter than a min heap? So my study guide problem I'll just say out loud is, try and do this with a min-oriented heap, and you will see that it doesn't work. Okay? And it's kind of an interesting asymmetry. You can cajole it into working, but it won't work nicely. So a min heap, if you use a min heap and just try and do this backwards using a min heap, it will break in a way that will become somewhat obvious. So something to try out whenever you meet with your study group to study with for the final. Try running in-place heap sort with a min heap and see why things break. It's kind of an interesting question. All right. Merge sort. This is an old friend. We've seen this before, and I'll give a quick demo. Now, this is a recursive algorithm where we split our array into 2 pieces. And by the way, today's theme is basic sorts. We're going to go through just the basic ones, and then we'll go into fancier ones next time. So merge sort works like this. This is a variant of merge sort, the only one you've seen, called top-down merge sort. First step, split your array into 2 pieces, waiting for projector to respond. So we split it into roughly two pieces, the left half and the right half, and then we sort both halves. Now this is a recursive algorithm, so I'm not even going to show you those steps. So let's sort the left and sort the right. Doesn't matter, it's recursive, we just trust that it works. That's the recursive leap of faith. So now that we've sorted both halves, we merge the 2 halves. To do that, we create an array, an auxiliary array, where we compare the smallest item in both of the arrays and take the smaller of the 2. So is 2 or 17 smaller? 2. So let's copy 2 over. Okay, so 2, you get copied, we advance the pointer on the pink side. So 15 and 17, who's smaller? 15, copy the 15. 17 and 17, which one do you want to copy? 17, good. I'll take the I one, I guess. All right. 32 and 17? 17. All right, so we keep going. When you're left with 32 and 41, 32 gets copied, and now I has nothing left to do, so we only just copy the remaining items in blue. All right, we already saw that in another lecture, but any questions about it? Yeah. How do you merge them? This process. So I created a separate array, and then I'm just stepping through them one by one. So that's the merging process. Oh, how do you sort them? It's a recursive algorithm, so you're just calling this algorithm on those pieces. So they just happen. Now, if you go all the way down like this step right there, what actually happened is it broke those into two pieces and broke those into two pieces until you had two arrays of size what? 1, and then there's nothing to sort, and then just merge them back. Yep. Yeah. But it's a recursive algorithm, so you actually don't need to know how it works. You can do it, you can not do it. All right. So the time complexity we already said in another lecture is n log n, and it also matches the pattern for the 4th runtime problem on midterm 2 this time around. And then space complexity is theta n. Now you might ask, is there an in-place merge sort? And this is an open problem in computer science. There is no known good merge sort that is in place. The algorithm is very complicated. I've tried reading it before. I've never understood it. And it's still n log n, the best known one, but it's slow. There's some constant factors that make it slow. So if you're bored, come up with an in-place merge sort. No one's done it yet. That's good. All right. So in-place merges is an open question. Okay. I have omitted the notes column out in discussion, but if I have time, I'll mention it at the end of today. Otherwise, I'll do it in the next lecture. All right, we have one more basic sort I'd like you to know about called insertion sort. And the basic strategy here. So far, we've seen 3 different ideas. We had selection-based sorting. We had selection-based sorting with a heap to speed things up. And by selection, I mean use the smallest or use the largest. That was the first idea. The second idea was merging items. The third will be inserting items. So insertion sort is going to be starting with an empty output sequence, add each item for the input at the appropriate location. Okay, so it's kind of, I think of it as the dual or the evil twin or something of selection sort, where when we insert 32, it goes into the array. All right. How about 15? Where should it go? Left or right of 32? Left. Good. Okay. What about 2? Where does that go? Left. Good. 17. Where does that go? Between 15 and 32. In the middle. Great. 19 in the middle-ish. 26 in the middle-ish. Okay. Where's 41 going to go? The right. Okay. 17. Next to 17. I'll put it to the right of the old 17. All right. Next 17 goes there. That's insertion sort. Any questions? Different way of doing things. All right. This approach is a little inefficient, though, because we have to keep resizing an array. Or maybe we're using an array list. Like finding the place in the middle of the array can be a little tricky. Okay, so that's insertion sort. So short, we did it in less than a minute. So that approach, if the output sequence has k items, then in the worst case, we're going to have to scoot all of our items over. So there's a way to make insertion sort better, which uses swapping. Okay, so this is the exact same algorithm, I promise. It's just written a different way. Okay, so that extremely simple algorithm we just came to understand, and hopefully you didn't blink, can be done this way instead. So what I'm going to do is this is an in-place version where I'm going to pick an item and say, hey, you are the traveler. This is item J is the current, or sorry, item I is the where we started, and J is going to track the item as it travels. What? What are you talking about traveling? I thought we were inserting. It'll make sense in a sec. All right, so 32, there's nothing to do, but when we get to 15, it is not in the right place. So what this version of insertion sort does is it says, hey, item, you're in the wrong place. Please go backwards until you're in the appropriate place. Okay, so 15, should it go backwards? Yeah. All right, so we move it backwards. So J is tracking where the traveler is. After I've done that, these 2 items are sorted, right? Because we sent 15 to be in its appropriate place, but we haven't even looked at these. How about 2? So 2's next up. Should it go to the left? Yes. Okay? Now at this point, I've temporarily broken my invariant that the left items are sorted, so 2 is going to keep going. Where does it go next? It goes left more. Those are now sorted. Now if you pause for a moment, you think, okay, yeah, I can see how this is the same thing as inserting, right? Because what I've done effectively is I've taken these 3 items and inserted them into a new array. It just happens to be the left half of this array. It's a cute trick, but not an obvious one. All right, how about 17? Next traveler. Where does it go? How many spots does it move? 1. Okay, good. 19. Moves over 1 spot. 26 moves one spot. 41, what does it do? Stays. 17, back, 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 back. All right, 17, back, 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 back. So this is insertion sort. It's just done in a funny way, where you have a traveler that goes backwards, and that's often what computer science is about. It's about achieving your simple objective, sometimes in a somewhat oblique way. Okay? All right. Any questions about this variant? Yes. Yeah, that's a great question. Why are we learning lots of sorts when there's probably one best sort? We'll talk about which one's best later. But that's a great point. There's more or less two best sorts, for two different circumstances. But we're using this more as a case study. All right. Different ways of thinking about this. Here's a couple more examples that we're going to close out by having you think a little bit about the runtime of insertion sort. Okay. So let's say we have the word potato, popular one in my lexicon. When we take P as the traveler, it does nothing. So I'm making it purple to say it's the traveler. No swaps happen. How about O? Well, O in English, LM and OP, it has to move to the left. So we end up with OP tato. Okay. Who's the next traveler? T. Does T move? No. T is bigger than P and O. How about A? What's A going to do? It's going to move all the way to the front. That results in 3 swaps. T, again, does not move. O is going to swap itself 3 times. So that is a little picture of the runtime of insertion sort in a way. Purple shows who was the traveler and how far they went. Black are all the items that item shoved out of its way to get to the front. So A shoved O, P, and T aside. Another bigger example, this one's just out of the optional algorithms textbook. We have sort example. If you sort this, the S doesn't move, the O moves 1, the R moves 1, the T doesn't move, E moves to the front. Yeah, that's 36 total swaps. So question for you, what is the runtime of insertion sort? It's a packed lecture and content. So I'm having you give me a lower bound and an upper bound. Remember, omega is that thing from discussion section. So you can read omega as at least and big O as at most. All right, I will spoil it. It's actually 2 answers, but the best answer I'd say is omega n, big O of n squared. So omega n means that the runtime is at least linear, and that's because every item needs to be the traveler and look at its next door neighbor. So in the best case, it would just be a sequence of green items all along the diagonal. And the worst case would be that everything pushes itself to the front. So it's either line versus triangle. And so a line has area that's linear, and a triangle has area that's n squared. Now technically, because of how big omega is defined, you could also say big omega 1. It's at least constant. I hope you all agree, but this is a tighter bound. Questions about this? Okay, not going to answer this. Have you asked this question? So I'm going to skip it because I don't have time. Okay, so this is my last observation, and then we're going to summarize. That insertion sort is a very good sort. So the question you asked earlier, why do we care about having many different sorts? Well, this is a funny special case. So if you have an array that is almost sorted, then insertion sort is very fast. So on the left array, turns out that in here, we have 5 inversions. And as a result, we'll only do 5 swaps. On the right, we have 3 inversions, so we only do 3 swaps. One thing I did not mention earlier, just a fact, is that anytime you swap 2 items that are adjacent in insertion sort, you're fixing 1 inversion. So there's a funny property of insertion sort, is that its runtime is proportional to the number of inversions. Okay. So I'm going past that one. And so, you know what I think I'm going to do? Just because there's not enough time to really digest this, especially because we're out of time, I'm going to kick off next time by comparing merge sort and insertion sort and talking about how this property matters. So, sorry, this lecture was originally timed not to have those 5 minutes of discussion at the beginning. Sorry I ran out of time, but we'll fix it and be done. We'll do this part again on Wednesday. Okay? So thank you, everybody, and I'll see you then. We have seen 4 sorts. Think about them all night. All right, bye. Do your homework.